Good morning, students. Let us discuss about the thrashing. I am Dr. R. Kylbury, Department of CSE, SRM ISD. So today we'll discuss about the thrashing. In the previous classes, we have discussed about the page replacement algorithm, where we are aware about how to load the frames, so that to identify whether there is a page fault or not, isn't it? So when a process is going for an execution, it expects some frames. If that frames are loaded, then that pages are exist in the page table. Suppose if the pages are missed, then there comes the page fault, right? So if this page fault rate is very high, then I can say this is a thrashing. So the operating systems in general, when we increase the number of process in a system, it increases the degree of programming. That we already aware, right? So when a degree of programming is increased, the CPU utilization also increased drastically. At a certain time, at a certain point, all your memory reside in the main memory. Those frames all are fully loaded. So at a certain time, the system will try to identify the free slots in order to go for loading the pages which may be expected by the particular process. So we need to call for the swap in and swap out process. So at that time, the time of the CPU is not yet utilized, so that the CPU utilization is drastically reduced. So it may try to take it into a empty, so which means that the process is busy on swapping the pages in and out. This is called as a thrashing. So which means a process is in thrashing. When I can say it is in a thrashing, if it is spending more time on paging rather than the execution, then I can say the process is in thrashing. So this thrashing will lead to low CPU utilization. It reduces the it degrades the CPU utilization, so that the processor assumes that there will be a empty slot, so that you can try to add at another process and then further grow for progress. But still the process are in the waiting in order to complete their task. Okay, so this is the challenge where we need to address. Okay, in order to avoid the thrashing, there are two methods or a model. The one is the working set model, the other is the page fault frequency model. First, if you take a working set model, it works based on the locality of reference. So locality of reference we'll see in the next slides. The page frequency model will try to identify the number of page faults. Based on that rate, page fault rate, we'll try to see whether I could increase the number of frames, or we are going to release the frames. Okay. So now we'll discuss about the locality before entering into the working set. What is the locality of model? So as I said, to prevent this thrashing, we need to provide a process with as many frames as it needs. So depend on the demand of the process, we need to increase the frames present in the main memory, right? So how do you know how many frames it needs? How do you came to know that this particular process is needed this many frames? So that is the big challenge, right? So in order to avoid that, or in order to identify, we are going to use the working set strategy. So it looks at how many frames a process is actually using. That will be first identified. This approach is called as the locality model. The locality model states that as a process executes, it moves from locality to locality. A locality is nothing but a set of pages that are actually used together. That is called as a locality. Okay. So a set of pages is going to be used. It's nothing but a locality, right? A program is generally composed of several dependent localities that may be overlapped. The the size of a locality, let us say a sum of size of locality, if this is greater than the total memory size, then which means that the demand is high than the memory available. There comes the thrashing. So we need to address this. Okay. If it is less than, then there is no possibility of thrashing because you have all the frames, all are hit, you can progress easily. So now we'll discuss about the working set model. As I said, the locality here we can say it's a working set window delta. A delta is nothing but the size of an window. That is the working set window size. Say it's a delta. Delta is nothing but a fixed number of page references. For an example, 10,000 instruction, 20,000 instruction, like that. See in this diagram, I have given a page reference table 26157777516231. Those are the page references are given. So in which I'm trying to fix the delta, that is the working set window size as 10. See from 2 to 1, the 10 frames are considered. The 10 pages are going to be loaded in my frame. Okay. So for the time interval of T1, the working set is going to hold only 1, 2, 5, 6, 7. The rest of the pages is not necessary. For the next time interval T2, the remaining 10 windows are 10 pages are considered, where I'm going to load only 3 and 4. The remaining are empty. So here I need a frame 5. Here 2 is enough, right? So this is the working set. So just we are trying to consider for the window size as 10 here. So in this case, the working set size WSSI of a process PI. Okay, for the particular PI, the working set size is nothing but a WSSI. The total number of pages referred in the most recent delta. That may vary, depends on the time to time. Okay. So if this delta is too small, say if it is very small, will not encompasses the entire locality. That is in our page replacement algorithms, we have considered the page size as only 4, right? So the frame sizes, if it is only 4, then there may be a more number of page faults. So if that page fault is too high, then I want to call for the swap in swap out process. If the delta is too large, which means that I have too many frames in my system, so that I can accomplish several localities. I can place more number of pages. Fine. So sometimes delta is also infinite. It will encompasses entire program. All the programs may also be expected. These are the different way or possible in order to handle the situation. Okay. So the demand D here is nothing but the demand, the total demand of a particular process PI. Okay. So that is nothing but the sum of the working set size I. If this D is greater than M, it means that the demand is high than the availability of a memory. So if it is high means there comes the thrashing. So what is the policy we want to maintain? If this D is greater than memory means then suspend one of the process so that the other process can load it on behalf of that page. Okay. If this demand is less than the M, it means that there is no possibility of thrashing. Okay. The second model is the page fault frequency. So the page fault frequency is going to identify the fault rate. Okay, so we are already aware about the as the number of frames gets increased, the page fault rate is going to reduce, right? The number of pages are increased in a system. It means that the page fault is going to be minimized. If the page fault rate is too high, so from this graph, the top, so the process has few frames allocated to it, so that there may be a more number of page fault. So the page fault rate is high in this, right? So if the page fault rate is low, which means that it indicates the process has too many frames, so that there are so many free frames or exist. Okay. So if the page fault rate falls below the lower limit, it means that frames can be available, so that the process is not going to use those pages, those frames, so that you can try to make use for the other process. So that if the page fault rate falls below the lower limit means frames can be removed from the process. Okay. Similarly, if the page fault rate exceeds the upper limit, then it means that the number of frames allocated by the system is very less, which means that the page fault rate is so high, so that a particular process will expect more number of frames from the system. So once you try to redefine the number of frames present in your system, then it can make use of a process in a better way. If the page fault rate is below the lower limit, frames can be removed from the process. Vice versa, the page fault rate exceeds the upper limit, more number of frames can be allocated to the process. From this graphical state of the system should be kept limited to the rectangular region formed in this diagram. So if you fix your page fault rate between the upper bound and the lower bound of that rectangular window, then you can try to say your system can able to work in a efficient manner. Fine. So hope you have understood the concept of thrashing, working set model and the page fault frequency model. Thank you.